In December 1972, astronauts Eugene Cernan and Harrison Schmitt climbed into their spacecraft and left the lunar surface. They were the last humans to stand on the moon. What followed was over 5 decades of silence in deep space. Without the massive budgets of the Apollo era, and with political priorities shifting back to Earth, human exploration beyond low Earth orbit effectively stopped. We didn't stop exploring entirely. We built the International Space Station, sent rovers to map Mars, and launched telescopes to look deep into the universe. But for half a century, every human mission remained restricted to an altitude of a few hundred miles. In 2017, NASA adjusted its long-term strategy. Instead of focusing on brief temporary visits, the agency established a doctrine for permanent lunar habitation. The goal moved from planting flags to building actual infrastructure. This chart shows the Artemis program's architecture scaling up in complexity. It starts with Artemis I in 2202 and advances to Artemis IV in 2098, where humans will land on the moon's south pole to construct a permanent base. Right in the middle of that timeline sits Artemis II, launching 4 humans on a looping trajectory around the moon and straight back to Earth. There is no landing on this trip. The primary objective is to prove that life support systems can keep a crew alive in deep space. This flyby provides the flight data and life support verification required before NASA can commit a crew to a lunar landing. In April 2023, inside a crowded stadium in Houston, the engineering goals of the Artemis program were assigned to 4 specific individuals. Mission Commander Reed Wiseman is a former test pilot and veteran of the International Space Station. His background is focused on maintaining psychological calm when experimental hardware acts up in a vacuum. Pilot Victor Glover brings experience as a U.S. Navy aviator. He previously flew on the SpaceX Crew 1 mission, and with this flight he becomes the first black astronaut to leave Earth orbit and head for the moon. Mission specialist Christina Koch holds the record for the longest single spaceflight by a woman, spending 328 days in orbit. As an expert in deep space biology, she is the first woman assigned to a lunar mission. Mission Specialist Jeremy Hansen is a former fighter pilot representing the Canadian Space Agency. His inclusion marks the first time a non-American will travel into deep space. The presence of these 4 individuals ensures that the first crew to return to the moon's vicinity represents a broader demographic range than the all-male, all-American teams of the Apollo era. Preparing for that flight took 3 years of constant repetition. They had to master entirely new control schemes, emergency procedures, and scientific protocols. The physical preparation happens long before liftoff. The crew runs exhausting spacewalk drills in massive underwater facilities to simulate weightlessness and practices manual capsule control while suspended in zero-gravity simulators. As launch day approaches, the team is locked down in strict medical quarantine in Houston. A minor cold or infection on Earth is an inconvenience. In deep space, without access to hospitals, it is a critical threat. Their survival relies on identifying and eliminating every possible point of failure while they still have the safety of gravity and oxygen. The Apollo landings were driven by Cold War competition, a solitary push by one nation to beat another. Artemis operates on a collaborative philosophy. This map illustrates the international coalition powering the mission. NASA is leading the charge, but the European Space Agency provides the service module powering the capsule. while the space agencies of Japan and Canada supply essential hardware, training, and personnel. Because of this global partnership, the crew looking back at Earth will include representatives from several different spacefaring nations. On April 1st, 2026, all that preparation met physics. A 322-foot-tall rocket ignited with enough thrust to break Earth's gravity and push a crewed capsule directly into the void. Just minutes after liftoff, Commander Wiseman looked out the window and radioed back. "We have a beautiful moonrise. We're heading right at it." With that single transmission, the 54-year gap in human deep space travel ended. The strategic shift from Earth orbit research to lunar infrastructure is now a flight-proven reality. It is April 1st, 2026. At Kennedy Space Center in Florida, the launch hardware for Artemis II sits secured on Launch Complex 39B, the exact pad used for the Apollo lunar missions. The primary physical hurdle for any lunar mission remains exactly the same as it was in the 1960s. Lifting a heavily loaded spacecraft off the Earth requires a massive immediate expenditure of energy to overcome the planet's gravity well. The standard aerospace solution for moving heavy payloads into deep space is low Earth orbit assembly. You launch the components and fuel in separate pieces and assemble or refuel them once they reach orbit. This 2D orbital map compares the multi-launch approach against Artemis II. NASA bypasses orbital assembly entirely, utilizing a direct injection trajectory, firing the vehicle straight toward the moon. Executing this with a crew and heavy cargo requires immense velocity. The delta V requirements are unforgiving. The hardware engineered specifically to meet those strict velocity parameters is the Space Launch System, or SLS. Standing 322 feet tall, or 98 meters, this vehicle rivals the size of the U.S. Capitol building and is capable of lifting an immense mass capacity directly from the pad. Secured at the very top of this stack is the Orion spacecraft, which will carry a crew of 4 astronauts into deep space. Once the countdown reaches 0, the crew embarks on a 10-day trans-lunar journey. Every piece of hardware, ounce of propellant, and breath of oxygen required for the entire mission is loaded right now. Eliminating the need to refuel in orbit means the initial launch must provide absolute maximum power. That single constraint dictates every mechanical design choice in the SLS architecture. To understand how the SLS achieves this, we have to deconstruct the vehicle's propulsion stack, starting at the central core stage. The core stage is a massive pressure vessel constructed to hold immense propellant reserves. It is filled entirely with cryogenic liquid hydrogen and liquid oxygen. At its base sit 4 RS-25 main engines. These burn that cryogenic fuel. They are highly modified and upgraded variants of the engines used to power the space shuttle. Mounted on both flanks of the liquid-fueled core stage are 2 solid rocket boosters, or SRBs. These SRBs are active strictly for the initial ascent phase. During the first 2 minutes of flight, they provide 75% of the total thrust required to lift the vehicle off the pad. To contextualize that power output, a single solid rocket booster on the SLS generates more thrust than an entire F-1 engine from the Apollo-era Saturn V rocket. When the 4 RS-25s and the twin SRBs fire simultaneously, the combined stack generates 8.8 million pounds of liftoff thrust. This bar chart quantifies that massive output directly against the 7.6 million pounds of baseline thrust produced by the Apollo Saturn V. That is a 15% net increase in liftoff power over the heaviest launch vehicle ever successfully flown. This 15% thrust margin provides the power required to lift the mass of Orion capsule, the European service module, and the 10 day crew manifest into a direct injection lunar trajectory. High above propulsion stack sits the orbital payload section, containing the Orion spacecraft. Orion is a biphasic system. It is not a standalone capsule, but rather a docked combination of a crew module and a service module. At 5 meters wide, the cone-shaped crew module contains 50% more internal volume than the heavily constrained interiors of legacy Apollo capsules. Attached directly below the crew compartment is the European service module. Built specifically by an international Airbus-led consortium, this section acts as Orion's primary power generation, thermal control, and life support bus. It also provides the spacecraft's main propulsion. The service module carries 1 main orbital engine, 8 auxiliary engines, and 24 individual reaction control thrusters for fine maneuvers. Every system on the vehicle ultimately serves one overarching survival constraint, enduring an atmospheric re-entry thermal load that peaks at 2,760 degrees Celsius. Following the unmanned Artemis I test flight, NASA engineers analyzed the base heat shield and discovered unexpected excessive char loss in the 8th coat ablative material. Instead of replacing the heat shield, NASA altered the re-entry trajectory, shifting to a steeper descent angle. Plunging at the steeper angle shortens exposure to peak heat, protecting the 8th coat material from excessive char loss, correcting the thermodynamic stress through software and flight dynamics. Rather than physical hardware reconstruction, allowed NASA to maintain the mission schedule without compromising structural safety. That exact structural integrity is put to the test the moment the countdown clock reaches 0. At T-0, the 4 RS-25s and the twin solid rocket boosters ignite simultaneously, bombarding the launch pad with peak acoustic energy. The 98-meter vehicle clears the launch tower in seconds, immediately initiating a roll program to orient its flight path downrange. 2 minutes into the flight, the SRBs exhaust their solid fuel. They trigger explosive bolts and execute a clean mechanical separation from the vehicle. With the boosters gone, the ascent profile now relies almost entirely on the sustained thrust of the liquid-fueled core stage, consuming thousands of gallons of liquid propellant per second. At T+8 minutes, the main engines cut off. The massive 98-meter core stage is physically jettisoned from the rocket, leaving only the upper stages and the crew vehicle. At this altitude, Orion pairs with the Interim Cryogenic Propulsion Stage, or ICS. Equipped with a single RL-10 engine, this module handles the precise orbital insertions. At T+17 minutes, the ICS fires for its first burn, successfully capturing Orion into a stable initial orbit around the Earth. Exactly 70 minutes into the flight, the ICPS engine ignites a second time. This burn executes an apogee raise, pushing the spacecraft into a highly elliptical Earth orbit. That apogee raise formally concludes the automated heavy lift phase of the flight. From this point forward, mission success depends entirely on orbital dynamics and active crew operations. At T+2 hours, Orion is stabilized in high Earth orbit. But before the spacecraft can safely transition to deep space operations, the crew must verify their manual flight controls. The Orion spacecraft physically separates from the now depleted ICPS upper stage, breaking the hardware stack apart for the final time. The discarded ICPS immediately serves a secondary function. Instead of just burning up in the atmosphere, it drifts nearby, acting as a passive spatial target for the Orion crew. This initiates the Proximity Operations Demonstration, a rigorous 70-minute orbital test designed to map and validate the spacecraft's exact handling characteristics in microgravity. Inside the capsule, pilot Victor Glover takes manual control of Orion's reaction control thrusters, utilizing active human input to manipulate the spacecraft's orientation. This first-person HUD overlay demonstrates the flight geometry. Glover steers Orion toward a precise 2-foot target on the drifting ICS, holding relative position and safely retreating. This manual verification is a prerequisite for deep space operations because lunar orbit lacks a GPS navigation network. The LEO demonstration proves that the reaction controls are responsive enough for the complex orbital mechanics required on Artemis II and IV, where astronauts will execute unassisted docking maneuvers with lunar landers. Once the test concludes, the ICPS drops back, deploys 4 International Research CubeSats, and enters a destructive trajectory into the Pacific Ocean. Successful completion of the proximity demonstration validates Orion's manual flight systems, officially clearing the crew to initiate the translunar injection burn. It is April 2, 2026. In the first few hours off the pad, the Orion capsule settles into an oval-shaped orbit around Earth, and the 4-person crew meticulously checks life support, communications, and navigation systems. Then comes the translunar injection, or TLI. The service module's main engine fires, violently accelerating the spacecraft to break out of Earth's circular hold. The angle of this engine burn requires absolute precision. If it is off by even a fraction of a degree, the entire trajectory fails. Mission specialist Christina Koch monitors the computer calculations in real time to ensure the timing is exact. This diagram shows the free return trajectory, a figure-8 path where Earth and lunar gravity lock the spacecraft into a continuous loop. It's an automatic safety net. If engines fail, gravity naturally pulls the capsule around the moon, swinging it back to Earth. Once the translunar injection is entirely complete, the engines cut out. The crew cannot turn the ship around. They're relying entirely on the strict laws of orbital mechanics to bring them home. Over the next 3 to 4 days, Orion crosses the 384,000-kilometer gap between the Earth and the Moon. Our planet shrinks down to a blue marble in the window, and radio signals take a fraction of a second longer to cross the void. To survive this isolation, the crew runs the Archer program. They draw their own blood and take cognitive tests to measure exactly how the human body reacts to deep space. In total weightlessness, muscles and bones deteriorate rapidly. The crew is required to exercise for 30 minutes every single day to fight off atrophy. Because iron barbells are useless in zero gravity, they use a superlight flywheel device, something smaller than a carry-on suitcase, to simulate resistance for heavy squats and deadlifts in space. They are doing all of this inside an extremely tight metal cylinder. When pilot Victor Glover stands next to the Orion capsule, the physical constraint becomes obvious. 4 humans share this tiny volume for over a week. Navigating to the moon requires massive rocket engines, but keeping a crew functional inside that space requires an entirely different branch of engineering. By day 5, the physics shift. This diagram shows the lunar sphere of influence, the exact mathematical boundary where the moon's gravitational pull overpowers the Earth's. Crossing that invisible threshold, Orion stops coasting and begins actively falling toward the lunar surface. Knowing exactly what is coming the next day, the crew immediately runs a complete spacesuit drill. They practice rapidly zipping into their pressurized survival gear and strapping securely into their metal seats. They run these tests now because tomorrow brings the lunar flyby. It is the fastest, closest, and most unforgiving maneuver of the entire flight. On April 6, 2026, Orion hits its closest approach. The capsule hurtles past the moon at an altitude of just 4,000 to 6,000 miles. This graphic illustrates that tight margin. Since the moon itself is roughly 2,100 miles wide, Orion is skimming by at a distance just twice the entire diameter of the moon. With no atmosphere to blur the light, the crew gets a razor-sharp view of massive crater fields passing directly beneath their windows. The spacecraft does not fire its engines here. Instead, it uses the moon's mass to catch the capsule and violently whip it around the far side. That gravitational slingshot gives Orion enough momentum to coast 7,500 kilometers beyond the far side of the moon. By riding that slingshot, these 4 humans travel further from Earth than any of the Apollo crews, setting a new all-time human spaceflight distance record before gravity pulls them back toward home. For days 7 through 9, Orion slides back down the exact same invisible track toward Earth. The crew resumes their deep space science. Because cosmic radiation heavily affects human rest, they run detailed studies on their own sleep quality. Mission specialist Jeremy Hansen and the rest of the crew continuously log this medical data, building the baseline research needed for much longer trips to Mars. But beneath the quiet of these scientific routines is a hard reality. They are drifting through a silent, weightless void, heading directly toward a brutal collision with Earth's atmosphere. On day 10, the return journey ends. Orion severs the heavy service module and exposes the crew capsule for atmospheric entry. The capsule hits the outer edge of Earth's atmosphere at 25,000 miles per hour. Air cannot move out of the way fast enough. The resulting friction ignites a 2,760 degrees Celsius plasma fireball that entirely envelops the spacecraft. The only thing protecting the 4 astronauts inside from incineration is this massive heat shield bolted to the bottom of the capsule. The thick plasma physically blocks all radio signals. For several agonizing minutes, the capsule falls completely silent, and Mission Control can do nothing but wait. Then the blackout lifts. The drogue and main parachutes deploy in sequence, violently slowing the returning capsule until it splashes safely into the Pacific Ocean for the Navy to recover. Returning a crew from a 10-day orbital gauntlet proves the Orion hardware works in deep space.